A2 Further Maths, Improper Integrals. So what I'd like you to do is just to start off with is plot the graph of y equals 1 over x squared. Alright, pause there, give it a quick sketch. Okay, so hopefully you recognise the graph of 1 over x squared. It should look something like this. And what I'd like to do now is, now you've got the graph in front of you, have a think about these three integrals. Just think about what the issue is or what the values of those three integrals could be. Okay, so when you look at this first one, you notice straight away this one's unusual because you've got infinity as one of the limits, and you haven't dealt with anything that's had infinity as one of the limits. So this one here is asking you to calculate the area or calculate the integral between 1 and infinity. What area would that be shaded onto there? And we can see that you just keep adding on and on and on and on because it's going off to infinity. This one, seems perfectly reasonable, 0 and 2 as limits, nothing wrong with that. But the problem is, of course, if you try putting 0 in as one of your limits, as you can see, that's an asymptote. So this one causes all sorts of issues again. It's asking for the integral between 0 and 2, but 0 is an asymptote, so therefore you can struggle to work out the area here. What's interesting though is the first one, which goes from 1 up to infinity, it's getting very, very small. You can see that it's getting very close, approaching that asymptote very quickly, whereas this one is obviously approaching a lot slower. So that might make a difference to what the actual value is. What's the issue with this one? Well, absolutely nothing, is there? It goes from 1, goes to -1. We can definitely get values there. But when we think about what the actual integral is working out, or what the area between those two is, we can see because it crosses this asymptote just here, we sort of got this area here that's just going off and off to infinity. So all three of these are what are called improper integrals because they involve working out limits either off to infinity or ones that work out from an asymptote or have an asymptote as part of them. So often when you find these answers, it could be that just because they go up to infinity doesn't mean the actual integral itself is infinity. You might find that it converges towards a certain value. Or in other cases, you might find that it just diverges because you keep adding on bigger and bigger parts. Right, so grab your notebooks then, please. An improper integral is one where the integrand is undefined at one of its limits. So it might be undefined because it's infinity, or it might be undefined because it's got an asymptote at one of those ends. You might also find that it has an undefined point partway through its limits. Okay, so it's not very clear on that explanation, but I'll write that down for you again in a second. So it's where the integral is undefined at one of its limits or at any point between the two limits. Okay, so let's go back to our example. Let's just think about just putting down those three examples for our notebooks. So one example could be that one of the limits itself is infinity. So if one of the limits is infinity, then it's clearly undefined at that point just there, so it's unbounded. So therefore that's an improper integral, or an example of an improper integral just there. You could have one that's unbounded like that, where 0 is an asymptote. So because it's an asymptote there, doesn't have a value, therefore it's unbounded like that. But also, just as like I said, just be aware that when you have ones that crosses an asymptote, for example, one that goes from -3 to 2, for example, because it crosses an undefined point at x equals 0, then that is also an improper integral. And those are the ones you need to be really careful with, because your calculator could potentially lie to you, because you could put those two values in, it could give you answers to those two values, but because it's not a continuous function, because it's got a point that's undefined partway through it, the whole thing will be an improper integral and you have to solve it a different way. I'll give you an example of one of those in a minute. Right, so let's have a look how we actually go about solving improper integrals then, because it's important to make sure that you find it using what's called a limiting process. So if I want to solve an improper integral, let's say, take that first one. So between 1 and infinity. Now this one's quite straightforward. And the reason why it's quite straightforward is because you've got infinity sort of blindingly obvious right in front of you. So you know which part of it is causing the issue. Okay, although you could have a situation where both limits are causing a problem, so you need to be aware of those. So in this case though, 1 is clearly defined. There's nothing wrong with number 1. That's not causing a problem, but infinity is the unbounded part. It goes off the end. Now what we wouldn't do, and where you'd lose marks, is if you just tried working out the integration of it and put in 1 and infinity as the two limits. What you've got to do is you've got to define a point, P. Okay, so we just use the P value, and that's defining a point that it's going up to. So we're going between 1 and P rather than 1 infinity. All right, so that's the first thing. Once we've done that, then we can solve the integral as normal. All right, so we can solve the integral as a normal integration, no issues at all, and we're going to get an answer, which in this case is minus 1 over x between 1 and P. Now then, once we've got this point, we can actually work out the value, of course, which is just going to be minus 1 over P plus 1. So that's the answer to the integral. If you used infinity in there rather than P, that's where you would lose all your marks. You need to be understanding that it's not just as straightforward as just solving it with infinity as if it's a number. You've got to make sure that you're showing this limiting process. Right, so at this stage, we're going to say what happens as P tends towards whichever limit we're looking at. Now, in this case, it's infinity. So we're looking at what happens as P tends towards that unbounded limit. And in this case, as P tends towards infinity, what happens to minus 1 over P plus 1? Now we know that as P tends towards infinity, this bit just here, the 1 over P part, is going to start tending towards 0. And so because 1 over P tends towards 0, minus 1 over P would tend towards 0, and you'd end up with 0 plus 1. So as P tends towards infinity, this bit just gets ridiculously small. This bit is your number 1, so it's getting closer and closer, but never quite reaches the number 1. So as P tends to infinity. So it's that part there, that limiting process, that's absolutely vital when you come to solving improper integrals. Without that bit, you would be losing the marks because you're not showing the understanding. So you must show the limiting process. You can also write it as lim P points towards infinity if you want to. You can write it like that, similar to how you've seen it in differentiation from first principles. So you can use a slightly different notation. Right, so once you've done that, then you can just say, because we know that P tends towards infinity, we can then solve the integral and say that it's equal to 1. But you must show this step just there. Okay, make sure you got what you know in your notebooks. Right, so let's look at the same sort of thing, but this time with 0 and 2. So I've noticed that when I put 0 into here, I get 1 over 0 squared. So clearly it's unbounded at 0. So there's a problem there. So once I recognise that 0 is the unbounded part, that's the part that I replace with my P. So this time 2 to 0 is going to change to 2 to P. I must replace my unbounded value by P. That's an essential part. Once you've done that, solve it as normal. We just did it. 1 over x is what it integrates to. Between 2 and P gets me minus 1 over 2 plus 1 over P. Okay, at this stage then, now I've got my answer, I can start looking at the limiting process. What happens as P tends towards 0 in this case? I'm trying to get from P to 0. So you're not replacing P for 0, you're talking about it being a limit. As P gets closer and closer to 0, what happens to this value here? So as P tends towards 0, minus 1 over 2 plus 1 over P, well, let's think about this. If P tends towards 0, 1 over a very small number is going to get a really big number. Okay, so 1 divided by 0.000 something is going to get very, very big. Really, that's going to overpower the minus a half. So the whole thing is going to blow up to infinity. Because that bit goes to infinity, the whole thing will go to infinity. So in this case, this integral just here is undefined because the whole thing just diverges off to infinity. Okay, again, get down what you need in your notebook. Okay, so what I'd like to do is just have a go at writing it down in your notebooks and think about what the issue is. Okay, so if you didn't spot what the issue is, you might be thinking, well, 3 is fine. Yeah, you could put 3 into that, get a value. You can put -6 into it, get a value. No issues at all. All right, both of those values would be perfectly reasonable because you're squaring it at the bottom. It's not a negative answer under the square root, under a cube root, or anything like that. It's perfectly reasonable. But the issue comes from when x equals 2. When x equals 2, you're going to have an asymptote occurring here. 1 divided by 2 minus 2 is 0, so 1 divided by 0 causes an asymptote. And most importantly, 2 is between these two values. So it's an improper integral, not because these two values are undefined, but because there's a value in between them that's undefined. So therefore, I've got to use improper integrals to solve it. So it's noticing that. It's not as straightforward as it looks. So the first thing I want to do is just make a note of that for the examiner and say, look, I can see the issue. The issue is x equals 2 is undefined. So therefore, that's where I'm going to have to use improper integral skills. What do you do then? Well, if you imagine that x equals 2, just there is your asymptote, we can't define x equals 2. But we do need to work up to number 3 and down to -6. So what we can do is we can split this integral up. We can look at what happens from -6 up to the asymptote at 2, and from the asymptote at 2 up to number 3. So we can look at it as two separate integrals. So that's what we're going to do now. We're going to investigate it either side of the number 2. So we can split it up. So the first one I'm going to look at is 2 up to number 3. So I'm looking at what happens from our value of 2 up to number 3. Now what I'd like you to do is have a go at doing the integration yourself. See if you can sort that out. So pause there, have a go at integrating it yourself. Okay, so let's see if you solved your integration. You should have said it's substitution. So I'm letting x equal minus, let u equal x minus 2. That's quite nice. You need to be careful though, because the x value when differentiated just goes to 1. So du equals dx. So that makes it nice and easy. So therefore, all I'm solving then is u squared to the power 3. So of course that's 3 over 2. I'm also just being very careful because now that I'm dealing with it as du, not dx, then I'm changing that to p minus 2 because the x value was p. So be careful with your substitution. Once I've done that, then I get 3 lots of the cube root of u. Right, because you can just write that as minus 2/3 between 1 and p minus 2. Substitute those in, gets me that value just there. And now at this point I can investigate what happens when we get the p-value tending towards 2. So this is what I meant earlier on about writing it as a limit like this. This is nothing wrong with this. So the limit as p tends towards 2, what's going to happen as p tends towards 2, you've got a number really close to 2, take away 2, is going to get you pretty much 0. So that part there is going to get you pretty much 0. The cube root of a number that's pretty much 0 is 0. So therefore the whole thing will be 0. What does that mean about this? Well, it means that the limit of that as p tends towards 2 is going to get you just 3. Okay, but it's important to show this limiting process. I keep repeating myself, but it's showing how important it is to make sure that you're clearly showing the limit of the equation. Okay, so that's part of it done. We've done the p up to 3. What we also need to do is do the other value down to -6. Right, so I'm just using q because I've used p already, and this is a different number. You think about the p value, that was on the other side of it. This is a different value, so I'm using q. I do the integration as I did before, blah, 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 in terms of du. I've got the value of that already, so I don't need to repeat loads of work. And when I substitute these values in, this time, I got this around. Oh, that looks messy, but don't forget it's a cube root, so that's okay. The cube root of minus 8 is minus 2. So therefore, when I've done this, I get plus 6, because it's minus 2 times minus 3 is plus 6. 3 lots of that. And even though we know the answer, let's just make sure we're writing out the limiting process just here. We know that the limit of this equals 0. That part equals 0. So therefore, the whole of that thing goes to 6. So we're repeating that limiting process just there. Once we're happy with that, we've done both sides of the asymptote. We've done down to 0 minus 6, which got you 6. We've done up to 3 on the other side. We can put... Okay, so now we've looked back at the original answer, and we see that we can split that up to either side of the asymptote. So we go from minus 6 up to 2 and 2 to 3. So the asymptote lies just there at 2. We've worked out the value of this one to be 6. We worked out the value of this one to be 3. So therefore the value of the original integral is going to equal 9. Right, so what I'd like to do is have a go at completing the exercise on 10C on page 244.